over time, which is driven by interactions of their constituent parts. In contexts such as engineering, social systems, dynamic systems modeling would allow us to predict, monitor, and improve complex behaviors in environments that are uncertain and have feedback cycles. Our integration of digital technology into healthcare will be robust, with cloud-based platforms that unifies digital operational and compliance workflows, which will be suited for the sensitive realm of mental health care, with applications that range from automated clinical documentation to secure analytics. With this transition into digital health, the clinical administration burden will be alleviated and support patient engagement and data security, which is key to ethical and effective mental health treatment in today's digital first landscape. A dynamic system is more of a methodological approach that captures the system's components. The models typically use elements such as talks, flows, and feedback loops that cause reinforcing or balancing behavior. An app for deployment in digital mental health system dynamics is opted for because of the presence of cyclical administration burdens, evolving compliance requirements, resource constraints, and dual effects of automation, which improve efficiency, potentially introducing new bottlenecks. There are some alternatives such as agent-based modeling, which will be useful for simulating individual heterogeneous actors and discrete event simulation, which fits logistical timing and system dynamics, providing the best lens for a holistic view. Furthermore, the operations will be designed to provide end-to-end automation of core mental health operations through integrated models for identity verification, secure documentation, incident reports, response, and compliance reporting. The design supports digital data integration, reducing manual handling for clinicals and ensuring that sensitive patient data remains secure and auditable at every step. The mental health sector does face pronounced shortages in clinical staff, heavy administrative overhead, and strict regulations, which is all compounded by growing diverse patient intake fueled by increased digital access. Modeling these operation flows as dynamic system clarifies improvement levers and vulnerability points.
My name is Brody McAfee, and I'll be doing slides 5 through 7. So here are the three models for our dynamic system. This model represents how automated efficiency models impact efficiency in digital mental health operations. On the left, we start with the patient queue, which represents clients waiting for intake or service. As automation increases, the processing rate improves, which means more patients are moved from the queue into the processed patient stock. This creates positive feedback loop, faster processing leads to shorter queues, and better resource utilization, which allows us to handle more patients with the same number of clinicians. However, there's also a balancing loop here. As automation grows, human oversight becomes limited, and that can slow progress or even reduce care quality if not managed properly. So the main takeaway is that automation initially boosts efficiency, but we reach a point where human involvement becomes the new bottleneck. The system needs balance, enough automation to improve throughput, but not so much that we lose effective oversight or empathy on patient care. The data trust and ethical risk model, we have our main feedback loops. So that creates higher trust, meaning more users, which means more richer data, better model accuracy, more trust. So it's just a loop that creates more trust over time. Our balancing is bias events or opaque data, trust loss, fewer users, reduce improvement rate. So this is ethical. As we want people to improve, it's going to improve the model. If people don't want to improve, it's not going to improve anything. Furthermore, we have a care quality and automation model. This allows just for quality care and for the model to automate work on its own. So our stock is automation level, care quality, clinician engagement. It's going to flow by automation increase rate and quality change rate. And then feedback loops. So the reinforcing will be more automation, faster responses, initial quality improvement. So this allows the more we get automized, the faster our results will get, and initial quality will improve. Balancing. So on the opposite side, too much automation means lower human empathy, declining care quality, reduced user satisfaction, pressure to restore human oversight. So we just need a balancing model that allows us to make steps that if the model is not working well, it will decline to even out eventually to go back to the reinforcing. For our next slide. It's loading. Our model limitations. So our model has simplified human factors. The model treats clinician behaviors, empathy, and decision-making as static variables. In reality, human motivation and fatigue fluctuate, which can strongly influence system performance. System feedback loops. Our model has smooth, predictable responses, but real-world systems often behave non-linearly. Small changes can trigger sudden overloads or slowdowns. The model assumes reliable, continuous data flow from digital tools. In practice, missing or biased data can distort results and lead to inaccurate projections of system behavior. Ethical risk factors like bias, transparency, and consent are simplified into a few parameters. The model and social nuances of patient trust can be fully captured in quantitative loops. The model does not account for regulatory changes or new compliance requirements, which can dramatically alter workflow automation and data governance over time. And also the model assumes automation continually increases efficiency, but real systems often experience diminishing returns as process approach maximum optimization. So those are some just the common flaws, but our model improvements, hopefully over time we can improve this way, is a six-step process. We integrate human factor data, which means future versions should include clinician workload, stress, and empathy metrics to capture how automation interacts with human behavior and quality care. We will incorporate live performance data from digital platforms like intake times and satisfaction scores to continuously refine model accuracy and responsiveness. Improve. We're going to add nonlinear behavior delays, and this will improve realism by modeling delays in implementation, learning curves, and saturation points where automation yields diminishing returns. We're going to expand ethical and regulatory parameters. This will be done by introducing variables for compliance, monitoring, transparency measures, and patient consent feedback to align with evolving data governance and standards. We will model hybrid workflow scenarios, simulate different balances between automation and human review to find optimal combination for speed and empathy. We're going to test with sensitivity analysis, run simulations that vary automation levels, staff members, and patient volume to identify which factors most strongly influence system performance.
This slide addresses the critical question of ethical representation. When we build a dynamic system like an AI-driven mental health tool, the model is only as ethical as its foundational assumptions. First, bias mitigation is paramount. Our dynamic system model, the AI, is trained on historical data. If that data is biased, for example, primarily featuring responses from one cultural group, the AI will perpetrate that bias, potentially leading to misdiagnosis or inappropriate intervention for other demographics. By clearly documenting our model's assumptions and inputs, we can identify and limit these three systematic biases. Second, transparency in assumptions is necessary for informed consent. In mental health care, trust is paramount. Users are giving us high-stakes, sensitive data. They must understand the underlying model and its limitations, that it's a predictive tool, not a perfect oracle. A clear explanation of the model ensures the patient is fully informed and ethically treated. Third, transparency combats model reducibility. We must ensure the model does not reduce a complex, suffering human being to a simple, deterministic score or data point, which is an ethical failure in any care model. Here we examine the dynamic system through the lens of the Christian worldview, specifically regarding human value. The compatibility is strong on the practical level. The Christian worldview emphasizes compassion and caring for the vulnerable. By creating an accessible 24/7 digital mental health tool, we are acting on the call to bear one another's burdens. The system extends the reach of care, which affirms human value by promoting healing. However, there is a potential incompatibility that must be carefully managed. The Christian concept of imago Dei, that every person is an image of God, affirms a profound, inherent, and non-reductive value. A dynamic system limitation is that it can only see a person as a set of inputs and outputs. If the system treats the individual as merely a collection of data points for optimization, it fundamentally misses their spiritual and relational complexity. The solution is ensuring the technology always functions as a tool to support human empathy and intervention, never replacing the holistic view of the human person. The system must serve the person, not reduce them. This slide details how we structured our team meetings to maximize performance. We prioritized a goal-oriented agenda. Our standard structure was simple: review progress, identify task conflicts, and assign next steps. This structure was highly deliberate. We chose it because the reflective thinking process is too slow for a CLC with tight deadlines. Our goal was speed and maximum efficiency per meeting. To promote dialogue and interaction, our team leaders, including myself, adopted a democratic leadership style. We avoided dictating answers and instead focused on facilitating debate until consensus was reached. The project's inherent demand for a unanimous vote also played a key role, as it forced deeper dialogue and interaction to overcome differences before any decision could be finalized. Finally, we used a blend of media. Zoom or Teams was used for synchronous meetings to maintain high personal connections. We relied heavily on shared Google Docs for asynchronous work, allowing us to collectively draft slides and speaker notes in real time, ensuring version control was maintained across the team.
Hello, my name is Hunter Caford, and this is my part of our dynamic systems presentation. Our team applied 6 core functions to enhance performance throughout the project. First, we set clear goals to define the scope of the dynamic system and assign tasks early on. Through planning, we organized a shared schedule that kept everyone aligned. During facilitation, we made sure that each team member's perspective was included in decision making. When it came time to implement, we divided tasks based on individual strengths, such as research, modeling, and presentation design. Finally, we regularly evaluated progress to maintain quality and consistency across our slides. These 6 functions helped us to stay organized, collaborative, and accountable. We relied on a combination of digital tools to stay connected and productive. Zoom was our main platform for weekly meetings, allowing for real-time discussion and screen sharing. For updates, we used Halo messages, which kept communication flowing between meetings. Our collaborative work took place in PowerPoint and Docs so that everyone could edit simultaneously, and all project files were stored in OneDrive to ensure easy access and version control. Finally, we maintained professional and positive communication, ensuring feedback remained constructive and that everyone was updated regularly. Through this project, our group developed a deeper understanding of how dynamic systems operate and how structured teamwork enhances problem solving. Each member contributed unique skills that strengthened the quality of our presentation. We learned the importance of consistent communication, ethical clarity and data modeling, and collaborative selection. This experience not only improved our academic teamwork, but also prepared us for real world situations where group coordination and integrity are essential. Finally, these are the key sources we referenced throughout our research and presentation. They provided foundational insights into dynamic systems, leadership theories, and team communication frameworks that guided our approach on the project. Thank you for watching.